Okay, so now we're going to enter combinations. Now let me give you a little bit of advice. Don't freak out on understanding the difference just yet between permutations and combinations, because you're going to need to see a bunch of problems worked that use several different techniques. So you need to wait till you get to a problem set and start trying to figure them out, or see examples to figure out which is which. But I'll do my best here to explain it. So to introduce the concept of combinations, let's use an example. So I'm going to use the math example, but a little bit differently. Suppose we have 4 sons. Let's say their names are M, A, T, H. So one's named M, one's A, and one's T, and one's H. They're near the same age. And we win 2 tickets to the World Series. Okay, now I'm wondering how many ways can I send 2 of the 4 sons to the game? So in other words, we want to know how many 2-son subsets are possible. Because the order that I select the 2 sons doesn't matter. They still get to go as long as they're in the group. Now, and obviously I can't have repetition. Repetition would be silly because I'm not going to send son M and son M to the game. He's not going to use both tickets. So we could do the exhaustion method. Well, we could send M and A, but notice MA and AM would be the same, so I don't say AM. We could send T and M, but I'm not going to say MT because that would be the same. We could send H and M, but not MH because that's the same. TA, but not AT because that would be the same. HA, but not AH because that would be the same. HT, but not TH because that would be the same. So therefore, those are the possibilities. 1, 2, 3, 4, 5, 6. So there's 6 possibilities. Each of these is a 2-person combination of the 4 letters or 4 names. A combination is simply a subset. The order of the selection is irrelevant. Because if I send M and A, what do they care about who I gave the first ticket to, as long as they both get to go? If we had more tickets, I could say how many 3-son subsets could I send. Now if I had 4 tickets, then it wouldn't really make much sense to even make it a problem, because if I want to know how many 4-son subsets I could send with 4 tickets, then that would just be 1 set, so I'd just send them all. Alright, let's go on to a combination definition. A combination of a set of n distinct objects where you take R at a time without repetition, so again, repetition does not apply, is an R element subset of the set of n objects. So here, instead of arrangements, we're looking for subsets. So we're not looking for the number of arrangements within the subsets, just the number of subsets. The arrangement or order of the subsets does not matter, like the example above. MA and AM is the same subset. So therefore, order does not matter, and repetition was not allowed. And actually, each of the 12, why did I say 12 here? Each of the 6 code words, oh wait, that doesn't even go here because that was for the permutation example. So let's scratch that off. I guess I copied and pasted and that got carried on. Okay, so anyway, each of the 6 elements I have here, each of these is called a combination, is what I'm trying to say. MA is a combination, TM is a combination, HM is a combination, TA, HA, and HT. All of those are called combinations. Okay, let's list all of the 3 object combinations of this set. Well, let's list 7, 3, and let's just list the first 3. There's a 3 object combination. So 7, 3, 6. Now, would 7, 6, 3 be another one? No, because that would be permutations. 7, 3, 6, we're just looking for the subsets. So 7, 3, 6, no matter how you arrange them, would be the same combination. And then you could do 7, 6, 4. You could do 7, 3, 4. You could do 3, 6, and 4. And so there are 4 combinations. So there's 4 possible combinations, 4 possible subsets of 3 objects taken from 4. Example. A lawyer must select 4 jurors from a set of 6. Ask yourself, can the jurors be repeated? No, you can't choose the same juror to sit in 2 different chairs. So repetition is not allowed. Is the order relevant? No, the jurors are just being selected. They're not put in any particular order. So this is a combination question. So we need the combination formula to determine the number of combinations. And so now let me give you the combination formula. So if you have a total of n objects and you want to know how many r object combinations there are, then the formula is n factorial divided by n minus r factorial, then multiplied by another r factorial. So the bottom is divided by an extra r factorial if you compare it to the permutation formula. I won't make a big deal out of this, but I will tell you this. What this r factorial does is it divides out all of the arrangements. So it removes all of the arrangements of the objects and just gives you the number of subsets. And over here some other ways that combinations can be written. This is sort of a shorthand notion with the parentheses. Okay, so go back to my jurors. I had 6 jurors, but I only want to select 4 of them. So let's see how many choices I have. 6 factorial over 6 minus 4 factorial, 4 factorial. So that'd be 6 factorial over 2 factorial. Where the heck did the 3 come from? 4 factorial. Hang on, let me fix that. Okay, so I may have lost my place here. I apologize if I did. But below is the formula for combinations. Okay, so NCR, that would be n objects selecting how many r element subsets can we select out of n objects. So that would be n factorial over n minus r factorial, then divided by another r factorial. Now that r factorial actually divides out all of the permutations and basically converts it to combinations. You don't have to fully understand that, just know the formula. These are just some other ways that combinations could be written. So you can look at that. Now up here I had a juror selection example, and for the juror selection example we had 6 jurors total and we had to choose 4. And it was a combination problem because I didn't care about the order of selection, I just wanted to know how many subsets were possible. So that would be out of 6, select 4. And so what I end up with, for using the formula for combinations, I get 6 factorial over 6 minus 4 factorial times 4 factorial, which is 6 factorial over 2 factorial, 4 factorial. And then I can write 6 factorial as 6 times 5 times 4 factorial. Then I can cancel the 4 factorials. And let's say I canceled it, so that shouldn't be there. And then I have 6 times 5 over 2 factorial, which is just 30 divided by 2, which is 15. And so that's the answer that you get there. So that means there's 15 subsets of 4 jurors that are possible. And this kind of shows you a little bit on how to find the combination key on the factorial. Let's see here. I think this is messed up right here. So let's just say this. For practice, you can try what I did up there. You can do 6C4 and make sure you get 15 for that. Okay, so you can use that as your check. Okay, now here are some examples that would lead to combination formula. How many ways could you select 3 people from a group of 10 people? So for example, if you had 10 people and you wanted to choose a committee of 3, well, in a committee you don't really care the order of the selection, so that would be a combination, and so that would be 10C3. So you want to know how many 3-person subsets you can get out of 10, and that's actually going to be 120. Now another example would be, suppose you had to choose a sample of 5 products from a group of 15 on an assembly line. Well, if you want to know how many 5 product samples you could choose, then the order doesn't matter. You just want to know how many 5 product subsets there are. So you could do 15C5, and that will come out to 3003. And then I like this example. like if 5 people are in a home and you want to know how many hugs there are when everybody gets ready to leave, then, well, 2 things we would assume. First of all, no repetition, because you're not going to hug yourself. And the order doesn't matter, because if A hugs B, that's the same as B hugging A. So it would be a combination problem. So out of 5 people, how many ways could you pair 2 of them up? So in other words, how many 2-person subsets can you get out of 5 people? And that answer would be 10, so that would be 10 hugs. Another way to think of that is, instead of 5 people, suppose you have 5 teams, and each team has to play each other once, and you wanted to know how many games you're going to have to schedule. Well, you can use combinations to determine that you have 5 teams, and you want to know how many ways you could pair, how many different pairs you would have to have for each team to play each other one time. And so 5 choose 2 would be 10. Okay, this is just a couple more examples. How many ways can 3 runners be selected from a field of 5 contestants? Well, nothing here implies that the order of selection matters, so that would be a combination, 5 choose 3. How many ways can 2 men be selected from a group of 8 men to be on a committee? Well, again, order doesn't matter, so that would be just 8 choose 2. Now, the special cases of combinations, I'll go over these real quick. If you have n choose n, that's 1. So if you want to know how many selections of 4 people out of 4 people there are, how many subsets, that would be 1 subset. If you want to know how many subsets of 1 less than 4 out of 4 people, like 4 choose 3, then that's always going to be n. So that would be this number here, 4, because n choose n minus 1 is always equal to n. Also, n choose 1 is always equal to n. So if you wanted to know what is 8 choose 1, that's going to just equal 8. And then just like the 0 for the permutation case is the same for the combination case, 8 choose 0 is always 1. Now you can read what I said here about special cases. It's not really important to memorize them. So, but you know, they're kind of neat if you do have them memorized. So how do you know when to use a permutation or combination? Well, first, only use them if repetition is not allowed. If repetition is allowed, you have to go back to the multiplication principle. Then once you've determined repetition is not allowed, to figure out if you use permutations or combinations, do this. Take a subset, then rearrange the subset. If you get something new, that tells you that order matters and it must be a permutation. If you don't get something new, then order doesn't matter and you're just interested in the number of subsets, so it's a combination problem. Here's an example. You have 9 families you would invite to a wedding. Unfortunately, you can only invite 6. How many different sets of invitations could you write? Well, this example is actually a combination problem because you have 9 families and you can only choose 6, and the order that doesn't matter. They're not going to be ranked in any order or anything like that. So you just want to know how many possible choices you have, so you just calculate 9 choose 6 and get 84. Okay, here's an example of a permutation and a combination side by side. Suppose a senior class at a high school consists of 40 students. How many ways could we assign the positions of president, vice president, secretary, and treasurer? Well, this would be a permutation 40p4 because since we're assigning them to positions, then the order matters. So we would have to calculate a permutation 40p4. And on both these examples, repetition is not allowed. The second example, how many ways could we select a group of 4 to serve on the committee? Well, that's different than the first example because in this example, I'm not interested in the order that they're selected. I just want to know how many 4 student subsets I can select. So that would be 40C4, and because order is not relevant. And then I calculated those on a calculator. I'm going to do one more video on this section, which is going to have sort of a mixture of different types of counting properties that will involve properties from all the different counting techniques that we've discussed.